Okay, in this video we're going to start taking a look at satellite motion. So first of all, what is a satellite? Well, satellite is simply an object that orbits. So when we say orbits, I mean it moves around in a circular or nearly circular. Another object. So, for example, the moon orbiting the Earth. Or on a bigger scale, the Earth orbiting the sun. So in each of these cases, we would say the Earth, in this case, is the satellite of the sun. The moon is the satellite of the Earth. Now, how do we begin to think about these satellites as being in free fall around the Earth? So let's picture our understanding of free fall so far. So let's say you were on a mountaintop and you set up a cannon. And you fired a cannonball. And you fired it with some horizontal velocity. We could use projectiles to model that cannonball as an object that will be accelerating downward due to the force of gravity while it's in the air, and it's going to land some distance away. Now, if I increase that initial velocity, I'm going to increase the horizontal distance that the object travels, or the cannonball travels, but it's eventually, because it's under the influence of gravity, going to be pulled down towards the ground. Well, now imagine if I fired this at a really high initial velocity, so high that we have to take a new view of the Earth, right? Let's zoom this surface of the Earth out. So we have a picture of our curved Earth. And here's our little mountaintop, and here's our cannon. Okay, so this cannonball was fired with such a strong initial velocity that as it fell to the Earth, the curvature of the Earth also fell beneath it, so to speak. So it kept going and going and going and going and came back right to where it had started. If that was the case, this object has now become a satellite of the Earth. All right, so the way we have a satellite being in free fall is that it's constantly being accelerated back towards the Earth as it goes in its trip around, as it orbits. It has a velocity that's tangential to the curved path at every given point. So I think you can recognize this as a form of circular motion due to a centripetal force that is F sub g, right? The force of gravity pulling that object back towards the surface of the Earth. So we can say, what is a satellite? It's in free fall around the Earth because the force of gravity is constantly pulling it towards the center of the Earth, but it's moving at a speed based upon its radius, how far away it is from the center of the Earth, in which it's going fast enough to kind of hug along the surface of the Earth, or at whatever elevations it's at, and constantly fall and fall and fall and fall and fall, and never go too fast to be shot out of orbit, never go too slow to fall down and hit the Earth, but should be right at that perfect speed so that it maintains the circular orbit. So we've already talked about this a little bit. What force accelerates a satellite? It really is the gravitational pull, and this is always towards the center of the orbit, which also is the center of the mass that's being orbited. In this case, that's the Earth, right? So what happens is this direction of the force towards the center of the Earth is also the direction of the acceleration relative to the orbit. So if it's being pulled towards the center, the acceleration is always towards the center. So this acceleration becomes a centripetal acceleration because it's towards the center of the path of this satellite moving in circular motion. So we have Fg becoming a centripetal force. We have the acceleration that it experiences due to this becoming a centripetal acceleration. So we have all the tools here to put together and connect the circular motion to the universal law of gravitation, which defines the magnitude of that force. Now, how do we measure the radius? We've mentioned this a couple of times. Excuse me. This is always center to center distance between the satellite and the object it's rotating about, which is center of mass to center of mass. All right, now let's put these pieces together. So how does the force of gravity on an object in orbit relate to the centripetal force? Well, we know that we can quantify the force of gravity between two objects as the universal gravitational, the mass of object 1, the mass of object 2, and the distance between those two squared. Well, if this is the mass between a satellite and an object that is orbiting, let's say a satellite around the Earth, for example, this becomes g, mass of the satellite, mass of the Earth, and then the orbital radius of that satellite squared. Well, since it's moving in a circular path, this force really is also a centripetal force, right? Force of gravity is a centripetal force pulling towards the center of the circular orbit. And we know from earlier in this unit that centripetal force can be modeled by taking the mass of the object that's orbiting, like the satellite, times its centripetal acceleration, which is also the speed squared over the radius. Now, this is the same radius in both the Fg equation and the centripetal force equation. It's the center to center distance is the r. So the same r used here is the r used here in my centripetal force equation. So this F sub c becomes mass times centripetal acceleration, which is just mass. And now this is the mass of the satellite. Let me be specific here. That's the object experiencing the centripetal force. And this becomes mass times the speed of the satellite squared over the orbital radius. So on the left side, I have my expression for centripetal force. On the right side, I have my expression for the magnitude of the force of gravity. And this is where it all comes together. Because what we see here is we have the mass of the satellite on both sides of the expression, and that cancels out. We also see that we have the orbital radius here and the orbital radius here, so this cancels out with the square. So what we're left with is this expression where the speed squared of a satellite is equal to the universal gravity, the mass of the Earth in this case, which is the object being orbited, and the radius of the orbit, or the distance center to center between the satellite and the object that's being orbited, which is the Earth. And so connecting circular motion with universal gravity gives us a way for solving problems and a way for modeling the motion of satellites using this expression. In the next video, I'm going to show you how this derives to a couple commonly used expressions for the circular motion and universal gravitation modeling of an object that's in satellite motion.